Thank you. So hello everyone, my name is Idriss Riouak. I'm a PhD student at Lund University in Sweden. And yesterday we talked about the efficient demand evaluation of fixed point attribute using static analysis. Can you hear me now? Yeah, better. So this is a joint work with Niklas, Jesper, Öqvist, Görel, Hedin, and Christoph Reichenbach. So static analysis is everywhere. And I hope you agree with me. And we can use static analysis to detect common bugs. For example, this piece of Java code is supposed to compute the nth number of the Fibonacci sequence. But with a good static analyzer will tell us that the assignment at line 6 is actually never used. So there might be an error here. Or, like for example, if we consider this other example, depending on the value of b, we might have a null pointer exception at line 4. And ideally, we would like to have a static analyzer that helps us to detect these kind of bugs while we're writing the code, and we don't have to wait, so that we don't have to wait like a couple of hours before getting the feedback from the static analyzer. And in order to do so, we need a static analyzer that is not only fast, but it should be able to evaluate the code in a demand-driven fashion. So demand-driven is, well, basically we just analyze what we actually need without computing the results for our entire code base. And it's basically the opposite or the dual of exhaustive evaluation, where we compute all the data, even if it's not required. So like think of yourself, you are in front of your editor and you want to analyze your compilation unit. You don't have to analyze the entire code base, but just the compilation unit or the method. And we used JustAdd, which support a formalism called reference attribute grammars, which is both declarative and it inherently supports demand-driven evaluation. So what is an attribute? Well, attributes were first introduced by Donald Knuth in 1968, and then they were extended to the object-oriented paradigm by Hedin. And let me explain you what is an attribute with an example. So again, let's consider our buggy Fibonacci example. If we parse it, we get this abstract syntax tree. And on top of this abstract syntax tree node, we can attach property, like we can derive properties. For example, let's say we want to know if this assignment here is dead. And by collecting information using other attributes, we can figure out that this assignment here is actually dead. And well, I said I use JustAdd. It supports reference attribute grammars. Example of project that use JustAdd are XtendJ, which is a Java 11 compiler. IntraJ, it's a static analyzer for Java 11. We have Blocky, we have Gem Modelica. But the main idea is that given a reference attribute grammar specification, we pass it through the JustAdd meta compiler, and what we get is the evaluation code. So the evaluation code is our actual XtendJ or our actual IntraJ. So let's go back to static analysis. Let's say we want to implement dataflow analysis. And if we open the Dragon book on the chapter about dataflow analysis, we will find this equation here, in and out equation. Those are equations for a backward dataflow analysis. And if we look at the dependency between the function that we have in this equation, we found that in depends on gen, which and depends also on kill. It depends on out. Out we call the successor, so it will like construct the control flow graph somehow. And it will also call or depends on in. And now that we have in and out, we have somehow to figure out and like to interpret this information that we have in these in and out sets. And for example, we can use a function or like an attribute to figure out what is in this out set. So we can use that to figure out if a variable or if an assignment is dead. And each of these functions can be implemented as an attribute. And this one is a static call graph static dependency graph of the attribute relation. But if we consider an instance of this one, we will have many more attributes many more instances of in and out and is that. So if we go back to our Fibonacci example again, we have the abstract syntax tree, and on top of that we can put this in and out in order to compute our data flow analysis. And I don't want you too much to focus on the details of this example here. I want you to focus on the shape of this graph. So if we look at in and out, this one. That in depends indirectly on itself. So we have a cycle. And in order to compute the value for that in, we have to compute a fixed point. And we can do that with reference attribute grammars by using circular attributes. Circular attributes are attributes which value may depend directly or indirectly on itself. And well, they are computed using this fixed point computation. We start with a bottom value and we keep iterating until we reach a fixed point. Now the question is, how can we efficiently compute a demand-driven fixed point attribute? And well, it's not easy. There has been a lot of research on how to compute circular attributes. The first, so in the original attribute grammars, circular attributes were not allowed. And then Farrow and Jones, independently, they introduced the concept of circular but well-defined attribute grammars. Boyland, in 1996, he presented he described how to compute circular attributes in a demand-driven fashion. And then Sasaki and Sasa, they described how to compute them for remote attributes, which are like a sort of reference attribute, but the reference are computed at compile time. And in 2003, Magnusson introduced the first algorithm for computing for circular reference attribute grammars, which is called the basis stack. In 2017, Öqvist presented the relaxed monolithic, which is an algorithm that is supposed to overcome the limitation of the basic stack. And today, I will present the relaxed stack, which overcomes the limitation of the relaxed monolithic. So since everything is built on top of the basic stack, I will start from there. So the basic stack allowed the coexistence of two different kind of attributes: circular attributes, which they trigger a fixed point computation, and non-circular attributes, which are evaluated. And once they are evaluated, fully evaluated, they are immediately cached and are ready to be reused. And the user or the developer has to annotate all the circular attributes manually. So if we consider our example here, the user will have to annotate both in and out, and everything that is not circular will be treated automatically by the compiler as non-circular. And this approach, or this algorithm, has two main limitations. The first one is that some attributes exhibit this circularity behavior for very few input. For example, in the XNJ Java compiler, the type attribute that we use for type analysis is circular only for few constructor, for like the lambda expression, but we will still pay a very expensive fixed point computation to compute the type analysis. And the second thing is that it becomes infeasible for very large projects. So here we have a snapshot of the XNJ Java compiler call graph. Each red dot is a circular attribute, and you can think about changing a single attribute may cause the changing like the circularity of other attributes. So it becomes really easy to introduce errors. And so Öqvist, he tries to overcome this limitation by introducing the relaxed monolithic algorithm. This algorithm allowed the coexistence of two attributes, again, circular, which trigger fixed point computation, but this time there has to be at least one attribute labeled as circular in each cycle. So we don't have to annotate everything. We just have to have at least one circular attribute in each cycle. And then instead of non-circular, we have agnostic attributes. Agnostic attributes, they behave as non-circular if they are evaluated, if they are not called inside a circular evaluation, and as soon as they are evaluated inside a circular evaluation, they become circular. So they behave as circular. So for this example here, the user will have to annotate one of the two attributes between in and out. Let's suppose decide to annotate in. And then everything else will be treated as agnostic. So we will have everything treated as agnostic. And everything works except that as soon as we have many circular attributes, it becomes inefficient. So the problem is that the algorithm cannot recognize. So as soon as we start with a circular attribute, or as soon as we encounter a circular attribute, all the downstream attributes will be treated as circular, even a diagnostic one. And this implies that we will compute everything, the circular evaluation in a big monolithic fixed point computation. So if we go back to our example here, we have the example as before. Allow me to extend it a little bit, where we introduce two extra attributes, is reachable and reachable, like to remove everything that is not reachable, let's say. Reachable is a circular attribute, and is reachable is an agnostic one. So now let's suppose that the first component with two attributes will require 20 iterations to converge, whereas the second one will require only 10 iterations to converge. And let's suppose that we query is dead. So here in green, we have things that are evaluated once, and in red, we have things that are evaluated 20 times. We start with is dead. Is dead will call out, that will call in. In here is a circular attribute. So from now on, the algorithm will treat everything as circular, and everything will be computed in this big monolithic fixed point computation. So everything will be computed 20 times, re-evaluated 20 times. So the gen will be computed 20 times, kill 20 times, even if they are supposed, like they are non-circular. So that's a huge waste of resources. So we propose, okay, and then we have isDead, which is then once everything is finished, that's cached immediately and returned. So that's computed only once. So we propose a new algorithm, which basically combines and allows the coexistence of all the three kinds of attributes. So we have circular, non-circular, and agnostic. So the basic stack algorithm was able to decompose this static strongly connected component in a smaller fixed point. But the annotation effort was high and made it impossible to build big projects. The relaxed monolithic, on the other hand, the annotation effort was very low, but inefficient in the case of many strongly connected component and circular attributes. So our algorithm can handle, can decompose these strongly connected components, but what about the annotation effort? Well, it's low with the use of static analysis. And the key idea is that if we know that a circular or an agnostic attribute labeled as circular or agnostic attributes are not in a circular evaluation, they will never appear in a circular evaluation, then we can treat them as non-circular, always. And I will give you an overview of the pipeline. So we start again with our reference attribute grammar specification. We pass it to the just add meta compiler that will generate the evaluation code. And so far, those are the same steps that we will do normally. Then we take an extra step. We pass the evaluation code to the CAT tool, which is the call graph analysis tool. From this tool, we'll find out what is circular and what is non-circular. And it will output this metadata file containing this classification of all the attributes that are non-circular. And then we pass it again to the same just add meta compiler plus some flags that allow us to read this metadata file. And we generate the optimized evaluation code. So going back to our example, So as I said, we start from the Java code that is generated by JustAdd. We construct the call graph, and this is the call graph, let's say. And then we compute the strongly connected component to find out which attributes are non-circular. And the idea is to find out all the trivial strongly connected components. So we have that is a trivial strongly connected component. This one is not a trivial component, and so on. So we have 2 non-trivial strongly connected components, but for everything else, we can just safely change the label from agnostic to non-circular. And then if we go back to our example where we have the 2 components that one will converge in 20 iteration and the other one in 10 iteration, and we query isDead. So we start with isDead, which will call out, that will call in, and then gen is non-circular, so it will be immediately cached and returned, so it will never be computed again. Kill, the same for kill. Then the successor will call is reachable, and this one is a special attribute because it's a non-circular attribute that calls a circular attribute. And this one will stop all the ongoing evaluation, allowing to start new fixed point attributes, new fixed point computation. So this one will converge after 10 iteration. So now is reachable can be computed, fully computed, and the same for the successor. So in and out will converge after 20 iteration, and isDead in 1. So now we have like the optimal solution where we don't have waste of resources or like, we don't compute things multiple times. Okay. So we conducted some experiments. So we compared the existing algorithms with our new relaxed stacked algorithm. And we didn't change the specification of the analysis, so we kept the same reference attribute grammar specification. And we did 3 case studies. Here today I will present only one. You can find the other 2 in the paper. But the first 2 I've shown, those are non-circular application, and they have shown that our algorithm does not introduce overhead. So it's sometimes faster, slightly faster, but not significantly faster in this case for like applications that are not heavily circular. And then for the IntelliJ static analyzer, which is a heavily circular application, we have the following result. So here the idea is that we compute the intraprocedural null pointer reference analysis for Java programs. And we computed the analysis on 8 different projects, starting from Antler, which is like 40,000 lines of code, to POI, which is 300,000 lines of code. And we measured both startup and steady state. And for startup, we have a speed up between 7x to 115 with a median of 15x. And in particular, like for XNJ, we have that it took for the relaxed monolithic 1,500 seconds. And that's because there was a method that was big, like 6,000 lines of code, and it didn't scale for the relaxed monolithic algorithm. And then for steady state, we have similar result. We have a speed up between 16x to 35x, and the median is 22. And we had to introduce a timeout there because otherwise the computation would have been, like the evaluation would have took so long. And what about demand-driven scenario? We also considered that because that was what we were interested in. So we randomly selected 10, 20, 50, 100, and 200 methods from each of these projects. And here we have the results from PMD. And we can see that for 200 methods, we managed to pass from 1.2 seconds to less than 0.2 with a speed up of 11x. And the results are proportional with the whole program analysis. So like, yeah. So to conclude, we introduced this new relaxed stacked algorithm. And then we use static analysis to reduce the annotation effort. So now we automatically find or reclassify circular and agnostic attributes to non-circular. And yeah, we compared the results with the basic stack and the relaxed monolithic, and we found out that for heavily circular application, our algorithm is faster. And we don't have to change, so it's completely compatible with the existing RAG specifications, so the user doesn't have to change anything. And like in the future, we plan to consider dynamic, like keeping track of dynamic strongly connected component, and also considering more advanced static analysis to improve the precision. And yeah, that's it. Here there is a link to the paper and a summary of what we did.
We have plenty of time for questions.
Cool work.
Yeah.
I really like how you were able to just reuse some tooling and apply it to the generated Java code to get the metadata that you needed. But what's the cost? Because you are first compiling your spec entirely, then you're analyzing the Java side, and then you're compiling it again.
Yes. So that's a good question. So we haven't looked at that aspect. We believe that, I mean, to get a speed up in the actual runtime, the user is like can spend like an extra minute or two in order to do this extra step and this extra analysis. And the user doesn't have to do anything, so it's completely automatized. And I think that's something that, I mean, you do it once per release, and then it should be doable, I think. But that's a good question. We should definitely look into it.
Thanks. It was a nice talk. So I was knowing a little bit about JSTAT. I was very curious where the static analysis was coming from, and it's from this external tool. I was secretly hoping that you had invested time to do analysis on the attribute grammars, but I know the whole point of demand-driven evaluation is you can just skip all that stuff. You don't have to worry about ordered attributes and all that sort of stuff. So I was like Jeff. I thought this was a very nice way to sort of handle it. But I'm curious about. I had two questions. So one is, do you lose any accuracy by doing the analysis on the generated Java code, that somehow, you know, you lose some information in the generation of the Java code and the analysis there is not as precise as it might be if you did it on the attribute grammar code?
Yes, I think like we don't lose precision from that side, like from the grammar. Okay, we could use some information that we have in the grammar to improve the precision. And so like sometimes we just do recursion on the tree and we don't have cycles, but our static analyzer, like the call graph analyzer, we consider that as a cycle. And so we could use information from the grammar to like improve the precision in that sense. Or like even considering a more advanced static analyzer, like instead of, right now we do class hierarchy analysis, very simple analysis. Like doing some alias analysis would improve quite a lot the precision. And I think this example of the recursion on the grammar on the tree will be solved by much more precise analysis. Yeah.
Oh, thanks. But I mean, you still have great speed up, so it's not like you've suffered. So my other question was more general about circular attributes. When you talk about fixed points, are these always least fixed points, or is there a sense that the value in the circular attribute is sort of monotonically growing in some way, or does that not sort of come into the discussion?
Well, if an attribute is labeled as circular, then we will start this fixed point computation. And we require the user to have a monotonic transfer function, and all the elements have to be all the partial values have to be in a finite lattice. So those are like a constraint that we put on on the developer. So yes, as soon as we encounter a circular attribute, we will start a fixed point computation. Might be a trivial one, like if we do reachability, for example, that will be converging once, like one iteration. But yeah, we will always start a fixed point computation. Yep.
You have to forgive me. I did not listen to the full talk. I've seen the abstract.
Yeah.
So I had a question on what type of analysis can you support? Do you support, say, analysis which have infinite lattice, like say constant propagation with distributive properties, or say range analysis which has an infinite lattice both sides?
So JustAdd was born as a metacompiler, so it was not built for like constructing analysis or static analysis. But now we are going more towards in that direction. So now we support circular attributes, and we can do analysis on finite lattice.
Will it support, say, an analysis which is non-distributive?
Which is not, sorry?
Which is non-distributive. Non-distributive, say,
yeah.
Constant propagation analysis is non-distributive, right?
Yes, I would say so, yeah, that should work.
Okay, because the traditional IDE type of analysis may not be able to support those. So just curious that.
That's a good question. To be honest, I don't know, like on top of my head.
Any more questions? So I have a final question.
Yeah.
Actually, I have two questions, but I think the answer boils down to the same thing. So first of all, I observed that because you're computing the strongly connected components, you're identifying the cycles.
Yeah.
So you're identifying the circular attributes.
Yeah.
So my observation would be that you don't need this kind of labeling, but at the same time, not every circular attribute would compute a fixed point. So is the latter the reason that you still decide to ask a user to identify circular attributes?
Yes, actually, that's a good. Yeah, exactly. I mean, otherwise, if we do everything automatically, we might introduce overhead, and we might be less precise than the user.
And just non-termination, I'm thinking.
Once again,
non-termination, potentially.
Well, okay, the user also has to specify this bottom value. Without the bottom value, the JustAdd compiler cannot find out what's the bottom value. And that's one reason. Let's see. I would say that's the main reason. And the performance also, like, yeah.
All right, thank you very much. Let's thank our speaker one more time.